Question 2 then is the other kind of MC delta T calculation that you get to do, where the reaction takes place in aqueous solution. So again, it's water that's being heated up, but it's being heated up by a reaction taking place by substances that are actually dissolved in it rather than by a flame. So people get uncomfortable with this and they feel that we're ignoring the stuff that's dissolved in there and just focusing on the water being heated up. And it is a bit of an assumption. If you're interested in it, there is an example which is explored in detail, which I've put in the extension questions, which shows that the assumptions that we make are not negligible. They do lead to some errors, but they're not actually as huge as you might think. And just one way of putting that in perspective is that if we look at this nitric acid, for example, it's 1.2 moles per dm cubed. You think that's reasonably concentrated solution. But if you work out the moles, in that 75 cm cubed, there are about 4.2 moles of water, and there are about 0.09 moles of nitric acid, which means in molar terms it's about 98% water. And that's why we get away with ignoring the other stuff, because a solution is mainly water with just a little bit of stuff dissolved in it, and it's really important to remember that in these kind of calculations. Before we go into that though, there is an extra complication here, which is that the substances that are reacting have not been added in exactly the right amounts to react, so there's an issue of excess to be sorted out. Okay, so the first thing it wants is an equation for the reaction. So we've got barium hydroxide and nitric acid. So we've got BaOH2 aqueous plus HNO3 aqueous, and it's the standard kind of acid plus hydroxide reaction. You hopefully know these patterns. Acid plus hydroxide goes to salt plus water. So the salt will be barium nitrate, which is that, because barium is 2 plus and nitrate is 1 minus. And there will be 2 waters, because we've got 2 oxygens to get rid of. And we need 2 of those to make it balance. Okay, so that's the balanced equation. Double check always that your equations balance. If this one doesn't, particularly if you get that number wrong or that number wrong, it's going to mess up your calculation. So it's not just a matter of, oh well, I might lose 1 mark for not balancing the equation right. It has much bigger knock-on effects than that. So that's really important. Okay, so then we have these data, and what we have to do is to work out how many moles of each substance we have, and hence deduce what's in excess. So the moles are easy because we've got a solution, we've got a volume, and we've got a concentration. So hopefully by now that immediately triggers you to think moles is concentration times volume in dm cubed. So for barium hydroxide, the concentration is 0.5, the volume is 75 cm cubed, but remember that has to be divided by 1000, so it's 0.5 times 0.0750, which is 0.0375 moles. And for nitric acid, we've got 1.2 moles per dm cubed times again 0.075 dm cubed, because we're adding equal volumes, 75 cm cubed to this to 75 cm cubed to that, which comes to 0.0900 moles. So you had to get those 2 numbers, and then you have to answer which one is in excess, and you've got to give a justification for that. You can't just say therefore nitric acid is in excess, because they're going to think you guessed. Nor can you just say, oh, there's more nitric acid than barium hydroxide, therefore nitric acid is in excess, because you've got to take account of the equation. So this is really important. Okay, it's not, excess doesn't just mean there's more of it being added. You've got to look at the equation and think, which one will there be some of it left at the end, and you have to explain that. So if you start, it doesn't matter which one you start with, but I'll start with the nitric acid just purely because the numbers are easier. So you've got 0.09 moles of nitric acid, and you can see from the equation that however many moles of nitric acid you have, you only need half as many moles of barium hydroxide, because 1 reacts with 2. Okay, so the moles of barium hydroxide needed for all of the nitric acid to react will be half of the nitric acid that was added. So we need to say that. Okay, so for all HNO3 to react, we need a half times 0.09 moles, which is 0.045 moles. Okay, so make sure you can see why that's the case. It just comes from that 2 in the equation. Twice as many moles of nitric acid will react as barium hydroxide. So if all of the nitric acid, all 0.09 moles of it are going to react, you need half as much, 0.045 moles of barium hydroxide. But we haven't got that much. We've only got 0.0375. Okay, but we have less than this, which means that nitric acid is in excess. Now in part C it asks us to work out how many moles of water will be formed in the reaction. So remember, this was our equation: barium hydroxide plus 2 nitric acid goes to barium nitrate plus 2H2O. What's really, really important is that you can see and understand that you can't use that number, which was the moles of nitric acid added, because we've worked out that that was excess. You can't use that to work out the moles of water, for the simple reason that not all of it reacts. That's what excess means. It means some of it reacts, but some of it's left over at the end. So if you use that number to work out how much water there is, you're kidding yourself, because you're pretending that all of it reacts when you know that's not true. So the golden rule is that you use the moles of the one that isn't in excess. Okay, so that's not in excess. And the golden rule is that you use this number to find moles of product. Okay, so if you hadn't got that idea from previous mole exercises that we did in the first term, that's an important one to get hold of now. That you call that the limiting reagent. It's the one that controls how much product you can have, because you've got more than enough of this. So that's not a useful number. Okay, so that's the one we work with. And the equation says that the moles of water, because of that 2, are twice as many as the moles of barium hydroxide. Okay, so from the equation, moles of water formed in the reaction are 2 times the moles of barium hydroxide, and 2 times 0.0375 is 0.0750 moles of H2O. Part D then asks us to find delta H of neutralization for this reaction of barium hydroxide and nitric acid. So for this, it's really crucial that you know the definition of that term. Okay, it wasn't just used as a sort of random term because this happens to be a neutralization. This has a very specific meaning which you have to know. So that's equal to delta H when 1 mole of water is formed in a neutralization reaction. Okay, so in other words, it's the amount of heat released if 1 mole reacts in our case we didn't have 1 mole reacting, so it's the total amount of heat released divided by the number of moles of water. Okay, so that means that delta H will equal minus kilojoules divided by moles of water. Minus is there because it's exothermic. In other words, the temperature increased in the reaction. So what we've got to do is to find that number, the number of kilojoules released in the reaction, because we've already got the moles of water from the previous part. So kilojoules comes from Q is equal to mc delta T. Now m is where you have to be careful, because remember, m is not the mass of the reactants, it's the mass of the water which is soaking up the heat that's produced, because you're measuring the temperature of that water. And yes, there's a little bit of stuff dissolved in it, but to a very good approximation it's mostly water in that solution, and therefore it's the water we focus on. And you use the idea that the volume in cm cubed is approximately equal to the mass in grams for an aqueous solution. And that's equivalent to saying that the density is approximately 1 gram per cm cubed. It's very important that you know that that's what you do for aqueous solutions, because sometimes they tell you to do it, but not usually. They expect you to realise that that's the approximation you have to work with. That is the density of pure water. Okay, so 1 gram of water does have a volume of exactly 1 cm cubed. So that's why it's a reasonable approximation, because this is mostly water with just a little bit of other stuff dissolved in it. Okay, so m, therefore we work out the total volume, which is 75 plus 75 is 150. So it's 150 cm cubed, therefore the mass is 150 grams. Okay, so you must always do that when you have these solution reactions. So that's equal to 150 times 4.18, and the temperature rise was 7 degrees C. The temperature rose from 23.0 to 30.0 degrees C, which is a rise of 7.0 degrees, which is where that comes from. So we can crunch those numbers together to get Q, which comes to 4389 joules. But remember, we need kilojoules, because this is the way we're going to calculate delta H. So that's equal to 4.389 kilojoules. We divide by 1000 to put that in kilojoules. So now we're almost there, because we just need to now put the numbers into this equation. So that's equal to minus, because it's exothermic, temperature went up, so the sign of delta H must be negative. So minus 4.389 divided by 0.0750, which was the moles of water formed, and that works out as minus 58.5 kilojoules per mole for the delta H of neutralization. Okay, so you had to do a lot more work on your own in that part. So there were 4 marks there, and you had to see your own way through it. So the important steps was, first you had to know the definition of delta H of neutralization. So that was important. You had to make sure that you used mc delta T correctly, particularly make sure you got m right, and that's the method you need to learn if you didn't get that, for getting m when it's a solution reaction. And then it was the usual business of this is your last step for turning the heat released into an actual delta H, so it's kilojoules per mole. So next in part E, it asks us for an ionic equation for the reaction. So starting with the full equation, which we've already got, we've got barium hydroxide plus nitric acid gives you barium nitrate plus water. So hopefully you're beginning to get the hang by now of how ionic equations work. They're not a cheat, they're just a way of accepting and recognizing in the equation that when you have an ionic solution, the ions are separate. The positive ions are no longer stuck to the negative ions. They wander around completely independently in the solution, so you can write them completely independently in the equation. That's the idea. So what you do is you look at each substance in the equation and you ask yourself, is that an ionic solution? And if it's an ionic substance by definition, metal compound, barium hydroxide solution, barium nitrate solution, then clearly it's an ionic substance, it will be ionic in solution. When it's an acid, again, you know that an acid is a proton donor. That means it breaks up to release H+ ions in solution. So again, you write the H+ ions separately because at least in part they will be, and in nitric acid actually virtually all of them are. But when it's a molecular substance, remember water is a simple molecular substance, it's not broken up into ions, so you don't pretend that it is, you just write the formula as the molecule. Okay, that's all you're doing. So, ionic substance, so we write the ions separately. So we have Ba2 plus 2 hydroxides. Okay, because 2 there means 2 moles of hydroxide for each mole of barium 2 plus. Same here, we've got H plus, we've got NO3 minus, and 2 in front means we'll have 2 moles of each. So 2H plus 2 NO3 minus. Here we've got Ba2 plus and 2 NO3 minus. Okay, from the barium nitrate. So all three of those substances, ionic solutions, so we've written the ion separately, and the only one we don't do that for is the water, because it's just a molecular substance, so we write the molecules as molecules, not broken up into ions. So then, you always look at the equation and say, right, are any of those ions on both sides? Because if they are, it just means they just sat there and watched while everything else happened. They weren't actually involved in the reaction, so they shouldn't really be in the equation. And you can see that that's the case for the barium ions, because they're there at the beginning and they're there at the end, so they drop out. And it's also true for the nitrate ions, because they were there at the beginning and also at the end as well. So what we're left with is 2OH minus plus 2H plus goes to 2H2O. And that's almost but not quite the answer, because what you always have to do at this point is check whether that's in its lowest terms. What that means is, can you divide through by 2 or by 3 or by 7 or something and still get whole numbers? And the answer is obviously in this case you could divide through by 2. So all those 2's will cancel out, and that just gives you this, which is the fundamental neutralization equation, which you always get for acid plus hydroxide reactions. Okay, so that is your ionic equation for part E. See how much simpler it is than that, and it's really important because it makes you realise that the fact you had something exotic, rather, like barium hydroxide, it doesn't matter. Any hydroxide would do, because any hydroxide plus any acid, that's all that happens in the reaction. So ionic equations are really insightful things because they show you what's really taking place when the reaction happens. Part F says hence predict a value of delta H of neutralization for sodium hydroxide and hydrochloric acid. And the important word there is hence. That means you're not supposed to be plucking a number out of the air. You're supposed to be plucking a number out in the light of what you've learnt here. So the obvious thing to pick up on was what it asked you for here was an ionic equation. So you're supposed to take the hint that hence is saying, okay, it's the ionic equation that's the key, so that's what we want for this one. So here's the reaction, HCl plus NaOH gives you NaCl plus water. Okay, again, everything aqueous. So if we do the ionic equation, we could do it the same way. We get H plus Cl minus plus Na plus OH minus. Okay, so all of those ions separate on the left hand side. And then the sodium chloride again, separate ions, Na plus and Cl minus. But the water, as we said, is just simple molecular, so that's just written as H2O. Look for the spectator ions, the ones that cancel out. Cl minus, there at the beginning, at the end, so off it goes. Same with the sodium ions, they're not changed either. What you're left with is H plus OH minus goes to water. In other words, it's the same ionic equation. And that's the point. So if you'd picked up on the hint in the question, that word hence, that said, right, based on what you've just done, how are we going to think about this? And the answer is, well, we've got to look at the ionic equation and compare them. And of course it's the same, because any hydroxide and any acid, that's all that ever happens. And if it's the same ionic equation, that means that the other ions that were different, sodium compared to barium, chloride compared to nitrate, it's neither here nor there, because they weren't reacting anyway. So delta H of neutralization, which is the delta H per mole of water formed, will be identical for both. Okay, if it's the same ionic equation, that means that there will be the same delta H of neutralization, because it's per mole of water formed, and the moles of water, they're formed by the same ionic reaction, so it's going to be the same number. So, which is minus 58.5 kilojoules per mole. Okay, so that was a really nice example of why ionic equations are so useful. Because without that insight, you would have just said, well, I've got no idea what this number is because it's a completely different reaction. But by doing the ionic equation, you realise it's not a completely different reaction. It's actually exactly the same reaction, so it has the same delta H. Question 3 was all about testing whether you had learnt the definitions for these particular kinds of enthalpy change. So enthalpy change of reaction, enthalpy change of formation, enthalpy change of combustion. You need to know what the specific meaning of each of those is, and if you got this question right, that says yes, you did know. If you didn't, it means that's what you've got to look at. So if you got this wrong, go back, read through the notes on those, and then have another go at it. So these were the data we were given. Part A asks us for the delta H of reaction, which is the enthalpy change, as it says here, when the number of moles shown in the equation react. In other words, because this is the equation we were given, delta H of reaction is the enthalpy change when 2 moles of hydrogen react. What we know from the experiment is how much heat was released when that amount of hydrogen reacted. So the first thing we've got to do is to work out how many moles that is. So in the experiment, the moles of hydrogen is mass over mR, which is 27.0 divided by 2, because hydrogen is H2, so the mR is 2, which is 13.5 moles of H2. So what we've got to do is to then work out, well, if 13.5, which releases that amount of energy, 7.72 times 10 to the 6 joules, but remember we want that in kilojoules, because we always work in kilojoules in chemistry, so we've got to divide that by 1000, which is 7720 kilojoules. Okay, so divide by 1000 is 7.72 times 10 to the 3, which is 7720 kilojoules. So 13.5 moles releases that much. We've got to scale that down and say, right, well, what would therefore 2 moles produce? Because that then gives us our delta H of reaction. So it may be obvious to you how to do that mathematically. If it's not, then probably the easiest way to think about it is like this. If 13.5 moles produces that much, then that means that 1 mole of hydrogen releases 7720 over 13.5 kilojoules. So 2 moles of hydrogen releases 2 times 7720 over 13.5 kilojoules. Okay, so we've just said, right, this is the amount from 13.5, divide it by 13.5, that tells you the amount from each mole. We want to know how much we get from 2 moles, because that's what's in the equation, so we multiply by 2, and we get 1144 kilojoules per mole is the amount released. But that's not quite the answer, because remember, this is an exothermic reaction. The heat's being given out, so delta H is negative. So delta H of reaction, which we write that, is minus 1144 kilojoules per mole is the answer. Part 2 then asks us for the enthalpy change of combustion. And again, that's a definition you need to know. Enthalpy change of combustion is the enthalpy change when 1 mole of hydrogen burns in oxygen. So of course you can see that's going to be easy, because we've just worked out the enthalpy change when 2 moles of hydrogen burn was minus 1144, so all we've got to do is halve it. Okay, so 2 moles of hydrogen gave us delta H of reaction, which was minus 1144 kilojoules per mole. So 1 mole of hydrogen burning will give us delta H of combustion, because it's defined when 1 mole of hydrogen burns, so it will just be half that, which is minus 572 kilojoules per mole is the delta H of combustion of hydrogen. Part 3 is now talking about delta H of formation of water. So again, this is a definition you need to know. Delta H of formation is the enthalpy change when 1 mole of a compound is formed from its elements. So in the case of water, it's when 1 mole of water is formed from hydrogen and oxygen. And you can see from this equation that however many moles of hydrogen you have, you get the same number of moles of water. So delta H of combustion of hydrogen, which is the enthalpy change when 1 mole of hydrogen burns, is the same as delta H of formation of water, because when 1 mole of hydrogen burns, you'll get 1 mole of water. So the answer is just the same as that one. Okay, minus 572 kilojoules per mole. But you can see that those numbers are easy to calculate once you know the definitions, but if you don't know the definitions, then obviously you would have no idea what to do. So enthalpy change of reaction, of combustion, of formation, and also of neutralization, which came in the previous question, those 4 you need to make sure you know what they mean and use those ideas in calculating the numbers that it asks you for.